So, let us again revisit this regression problem, but we will do that in the context of regularization. Okay. So, it looks like our journey through neural networks is approximation or solving the regression problem or classification or one or the other modes of applications, but we will revisit this regression problem again. Okay. So, consider the nonlinear regression problem. We have dealt with it many times already. So, same way I write di is f of xi plus epsilon I for points I equals 1 to capital N, where N is the data points and f is unknown, right, the same setup. And we assume that epsilon I is drawn from a zero mean white process with the covariance given by expected value of epsilon I, epsilon k. This quantity, this expectation is sigma square when I equals k and 0 else. Now, we have dealt with this regression problem earlier, but we will try to introduce regularization to the regression problem. So, let me set this up carefully. The goal would be to recover f of xi. That means I need to figure out what this f is approximately given the data set xi and di I equals 1 to n. So, I put this within a tuple. So, for which I need to bring in some regularity conditions. So, let me state that. So, let capital F lambda of x be the regularized estimate of this unknown function f of x for some regularization parameter lambda. And what this regularization parameter does? It adds a smoothness constraint to the function or the approximating function that you are trying to solve, right. So, E of f is our Tikhonov functional that we have dealt earlier. And this Tikhonov functional has two parts. One is the squared error of this deviation between the desired and the approximating function evaluated at the data point xi, and this quantity here is sort of a measure of fidelity to data. And then we have the other part. This is where the regularization comes into picture. We have a linear differential operator acting on this function, I would say f of x to be little more clear. I look at the norm where this function space resides, and this sort of gives us the smoothness constraint. Okay. So, with this, let us start with our averaged square error. Let R of lambda denote the averaged square error over a given data set between the two functions. One is this unknown function f of x that pertains to the model, and the approximating function, which is f lambda of x pertaining to the representation of the solution for some lambda over the training set, right. So, the only change I have here as against what I had in the regular in my discussion during the regular the only change I have between this setup and the setup I had during the regression basics was the inclusion of this regularization term, right, and that is the reason why I want to bring in this parameter lambda here in the subscript. Okay. Now, let us consider further with our analysis. So, R of lambda is now averaging the error I have between what I get from f of xi and this approximation f lambda of xi, right. F lambda of xi is the approximating function with the regulation constraint, and that is the reason why I bring this subscript lambda there, and f of xi is the unknown function, right. This is what I need to this is what I compute, and I call this as R of lambda. Now, f of lambda as a function of these data points can be written in this form. It is summation I equals 1 to n aki of lambda times di. Let me tell you what this means. So, I have my desired samples d sub I, and I combine them using some coefficients aki that depend on lambda to get the function evaluated at this point xk, right. This subscript k, observe carefully that this pertains to the data point. And I is basically some I have this running summation I equals 1 to n. This is some linear combination of the samples that I have, right. Now I can write it in the form of matrices. So I can write f lambda is my vector, put this bar here, is A of lambda, which is my matrix times this vector D, where I will define all these terms. So as we see through it, so f lambda is f lambda evaluated at x1 dot 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 evaluated at data point xn. This is a column vector n by 1, size n by 1, and then we have this matrix A of lambda, which is also called the influence matrix, and this is of the form A11 A12 dot 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 till A1n. It is an n by n matrix. Okay, it has n square elements, and this is called the influence matrix. Now D is this vector, which is what we are familiar with, which is D1, D2. You stack up all the desired responses, and that is what we have. It is an n by 1 column vector. Now R of lambda is basically the norm of f minus capital F of lambda, the norm square, and is the L2 norm, right. The norm is L2 norm. Now I omit the bar sometimes. So if I remove it, it is implied that we are meaning that it is a vector here, right. So I did not specify what small f is. So this f, as you can expect, this is nothing but f of x1 so on till small f of xn. Okay. So this sets the problem up. Now simplifying, R of lambda is 1 upon n, the norm of small f minus A of lambda times D, because capital F of lambda can be written as A of lambda times the vector D, and I look at the square norm of this quantity. Right. Now I also have my vector D is F plus E, where epsilon vector epsilon is basically the realization E1 epsilon 1 so on till epsilon n over those n data points. This is just a noise realization. Now let us simplify this further, right. So I will call I do not have any equation numbers in this setup. So maybe I will start with some numberings. So let me call this equation number 1, I call this equation number 2. Okay. So I plug equation 2 in equation 1, that is I express D equals F plus epsilon, and then I simplify this. So what I get is the following. So R of lambda equals 1 upon n, the norm of F minus A of lambda times this vector D, and I write d is f plus epsilon, and I need to take this norm square. So I have to expand this out. So I simplify a little bit before I expand. So this is going to be f minus a of lambda times f minus a of lambda times epsilon, this norm square, okay, and I can write it in this form 1 upon n norm I minus a of lambda times f minus a lambda times epsilon, okay. Now I can expand this out. So let us call this equation 3. Let us expand 3 and then we can write it in compact form. Now we have bunch of matrices times some vectors and stuff like these, and when you look at this norm square, it is a scalar quantity, and I can express this in a compact form. So what I do is as follows. So I can expand this, and this is straightforward algebra. I can write this as, I have this 1 upon n which is outside times norm of I minus a of lambda times f squared minus 2 upon n epsilon transposed a of lambda transposed times I minus a of lambda times f plus we have the norm square on the noise term, which is scaled by the influence matrix. So this is 1 upon n the norm of a of lambda times epsilon squared. Now we have this is what our simplification is, but we need expectation over r of lambda right. So when we take expectation over r of lambda, so this is 0 mean noise, so therefore the second term just sort of vanishes out, so it is out of the picture for us. So we have to compute the expectations over these two terms, which is term 1, which is I minus a of lambda times f, and then this other term, term 2. Right, and this term, let me indicate the middle term. Expectation over the middle term is 0. Right, so we just have to compute the expectations over terms 1 and 2. So let us simplify this. Now expected value of 1 upon n the norm of I minus a of lambda times f, this squared is, there is nothing random about it, so therefore it is just 1 upon n the norm of I minus A of lambda times f, this squared. Yeah, before we end the slide, small change here. We need to insert these braces. Term 2, we will have to do some jugglery. So, we will try to see what it simplifies to. So, let us consider expected value of the norm of A of lambda times epsilon, this squared. Now, I can write this as expected value of epsilon transposed times A of lambda transposed times A of lambda times epsilon. So, this is what I have. Now, I can, this is a scalar quantity, right, this norm square is a scalar quantity. So, I can bring in this trace operation outside, because trace of a scalar is essentially the scalar, but I will see how this trace can help me out. So, I have trace outside, trace of expected value of this quantity epsilon transposed A of lambda transposed A of lambda times epsilon. Now, I can exchange the expectation and trace the linear operators. So, I can do that. So, I have expected value of trace of epsilon transposed A of lambda transposed A of lambda times epsilon. So, I have this in this form. Okay. But you see the reason why I got this trace, because now I have a bunch of matrices and I want to do the trace of ABC. So, it is invariant if I do a trace ABC, BC, and I just do the cyclic ordering, it is invariant. So, therefore, I invoke that property. So, this is expected value of trace. What I do is I bring in A lambda transposed first, then I have A lambda, then I have epsilon, and I have epsilon transposed to the end. This is valid because of trace of AB is trace of BA, right. Now, this is slightly easier for me to simplify, because what I can do is I can pull this trace of A transposed A of lambda transposed times A of lambda. I pull this out and I do the expectation over this quantity here, and this happens to be my sigma square in terms of my covariance matrix. So, it is sigma square times trace of A lambda transposed times A lambda. This is sigma square identity. So, so this quantity is basically sigma square here. So, I get this sigma square trace of this quantity here. Now, so it's I can say that expected value of norm A lambda times f, this quantity square, the norm square is basically sigma square trace of A lambda transposed times A lambda. Well, this should be an epsilon, not f. So, we will make the small change here. So, therefore, I can simplify the expectation over r of lambda to be this quantity which is given as follows. But we still have a problem. Because the average error that we have computed is a function of the regression function f, which is unknown, and I am bringing that still, right. So, E of r of lambda is still a function of f which is unknown. Yeah, before we end the slide, we need to insert these braces as usual, so that it does not confuse us. So, for which we can formulate a reasonable estimate, of r hat of r of lambda, which is given by r hat. So, this is given by r hat of lambda equals 1 upon n. So, what I do is the f I replace by the vector d, and this is a reasonable estimate because we do not know f, right, and I want this estimate to be unbiased. So, I have to include an additional term. So, let me put this in final form, and I will leave this as an exercise for you to show that this estimate is essentially unbiased. Now, if you observe this equation, what we have is the estimate r lambda depends on the regularization parameter lambda, right. So, this depends on lambda. We missed this brace here, so just to put the braces back again. So, this r hat of lambda is basically expected value of r of lambda. This is just for clarity. Okay. So, therefore, if you minimize the average error over all possible choices of lambda, you can get an estimate for you can choose the right lambda that and eventually the right estimate. You may question at this stage, how do I choose that lambda? Recall, there is a connection between lambda and the influence matrix that you have, right. The influence matrix entries are dependent on lambda. So, therefore, if you directly plug in the parameters of the influence matrix into the Tikhonov functional and solve for the entries of the influence matrix, you in a way have figured out what should be the parameters that optimize the regularized cost. Okay. So, I am not saying that if you just plug in all the values Aij entries into your functional, you will be able to solve this problem. There may be additional constraints you may have to pose on the entries in the influence matrix to drive your solution towards a unique solution, right. So, I think this is a small detail, but I think the purpose of analysis of what we did was to show that you can start with a regularized cost function to the regression problem, that is, you can augment the regularization term to your regression cost, and then you can follow the mathematics in a very straightforward manner. I mean, it is just some algebraic simplifications. So, all you will land up with an estimate for this error, which depends upon lambda, what you are trying to that depends upon the geometry of the problem, what you really require, right, and that also can be optimized by feeding those parameters back into the functional and then set up the conditions for optimality and then solving for it. Okay. So, this sort of completes this sort of big picture about the regularization problems, where we have dealt with particularly from approximating function perspective and also from the perspective of the regression. So, we have evolved the regression problem from a simple regression model involving linear regression and logistic regression from the very beginning of this course all the way towards bringing in a regularized cost associated with the regression problem and then trying to optimize our solution towards this problem, and therefore, there is a role of neural networks in this problem. Okay. So, with this we will end this module and we will work further.